complete a simple series circuit which would carry a large direct current. Loose wire is resting between the poles of the magnet. There's also an ammeter in the circuit.
Good evening. Can you hear me? Okay. Okay, thank you. Okay, last week we completed the Kirchhoff law and all type of applications we discussed. You can try your tutorial questions. Okay. Yes, 3 tutorials for this lesson, right? Yeah, you have four tutorials. Yeah, the circuit papers we discussed all questions, and I given homeworks. And tutorial number 1, 2, and 3. Okay, now 70% of the lesson completed. You can try those questions as much possible. I hope to discuss, but I don't think to complete every question. Make it questions. You have more than 1,000 questions. Everything we can't discuss, but if any difficult part, I will explain if you request at the end of the lesson. And our Sunday class, I hope to get 4 theory lessons, and we're doing revisions only for these 2 months, February and March. We're doing revision only Tuesday. Sunday, as usually, we're doing our lesson. I hope to complete our electricity lesson coming Sunday. And within this week, electricity completed. And after that, we can start statistics, natural products, industrial chemistry, environment chemistry, cell structure. Then syllabus completed. And fluid mechanism. Okay, let's try. We have another 6 months: March, April, May, June, July. Only 5 months. Let's try to at least within 3 months to complete entire syllabus. Syllabus at least end of May, including ICT lessons. Then it is very easy. You can only revise everything and ready for the exam. After that, we have 2 months full time we can get for the paper discussions, model paper, past paper, prototype paper, everything. Hurry. Okay, last week we discussed about Kirchhoff laws. Give me a second. Where is our pen? Yes. Okay, we discussed about Kirchhoff laws. Okay, this is 6th week we doing electricity lesson. 7th week. We got 2 months for this lesson. That now enough. Okay, come to this part. Okay, this all about we discussed. It's Kirchhoff law. The current calculation methods. The Kirchhoff law is simple current calculation method instead of Ohm's law. Ohm's law we can apply only for simple systems. Simple, only for one battery circuit, for only one loop. But if it is complex circuit, we can use Kirchhoff laws first and second Kirchhoff laws to calculate the current. Okay. The heating effect of electric current. The heating effect actually I explained already. Okay, if you got the conductor, good conductor like copper, aluminium, conductor mean what? What's the meaning of conductor, Fatima? What's the meaning of conductor? Conductor. And semiconductors. Dehini? What's the meaning of definition of conductors? Conductors, semiconductors. What's the meaning? What's the difference? Yes. No. What's the basic? How we can classify it? Semiconductor, conductor, insulators. How we can classify it? Material which have the very good. No. Having high ability to conduct current. How it's coming this ability? No. Anyone still don't have the keywords. Conductors mean කොහොමද the ability again? Yes, due to huge number of free electrons in a unit volume. Huge number of free electrons in a unit volume. That's why we call they are conductors. Yes, very good, Kabi. It has maximum, we can't say maximum. It's a huge number. Maximum can be Kabi. No maximum, but the number of free electrons greater comparatively. Semiconductor, it's average, moderate level, right? Moderate level free electrons. Insulators, what's the definition of insulators? What's the definition? Insulators, what's the definition? Rehlan, what's the definition of insulators? Insulators, what are the examples? Pure water is an insulate. No current flowing. What else? Insulator, paper, rubber, plastic, they are insulators. What's the meaning? Rigiform. Kabir, what is the answer? This answer for which conductor, semiconductor, insulators? Your final answer? Dihni, what is the definition of insulators? Semiconductors, okay. I want insulators. Now you have to remember, you are the exam batch now. Don't have time to play. Yeah, it has very less free electrons. It has free electrons, but the amount of free electrons not sufficient to pass electric current. That's it. You should have a full idea. You can't say materials without free electrons, they are not insulators. Every material has some amount of free electrons, some minimum amount they have, but the amount not enough to pass electric current. The amount not enough to, not sufficient to pass electric current. That's a mean. Okay, however, conductors, semiconductors, insulators, now they are the difference. The number of free electrons is the difference. The number of free electrons. Hurry. Now, one initially in first or second day, as I remember, I explained about if I heat it, if I increase the temperature of conductor, what happened? What happened to the resistance? Resistance increasing or resistivity, rho value increasing. I think you can remember the resistance increasing mean the reason then conductivity decreasing, right? Conductivity mean what's the symbol for conductivity? What's the symbol for conductivity? Sigma, no? Okay, here I already explained same thing. I'm revising. Yeah, that's a sigma. That's conductivity. Okay, the resistivity increasing. When increase the temperature, the resistivity and resistance increasing, conductivity decreasing. Conductivity decreasing. Why conductivity decreasing? I think I explained. When increase the temperature, what happened? The molecule kinetic energy. Molecule kinetic energy increasing. But due to collision of new bonds, and it comes as barrier for electron flow. Yes. Yeah. The number of collisions and simply the molecule kinetic energy vibration increasing. Free electrons vibrations increasing. Due to that, the barriers increasing, the disturbance increasing. That's why disturbance for electron flowing increasing. My videos only therefore the conductivity decreasing electric with temperature increase. Okay, temperature effect already discussed. Okay, semiconductors, it is totally different. When increase the temperature of semiconductors, I already explained. When increase the temperature, the resistance decreasing, the resistivity decreasing because their bonds break down and number of free electrons increasing with increasing temperature. Due to these vibrations, number of free electrons increasing. Even in disturbed condition, now with vibration it disturbing to flow, but even in disturbed condition, when increase the number of free electrons, the conductivity increasing. The conductivity increasing. It's not 6 sigma, okay. It's conductivity increase. Okay, when increase the temperature of insulators, what happened? What's the effect? How they behave? Increasing or decreasing? What do you think? The resistance increasing or decreasing? Resistance increasing or decreasing? Resistance increasing or decreasing? I already explained. Yes, no any change. Resistance, it's not an effect. Therefore, conductivity also not changing. Okay, that's a simple story. The heating effect of conductivity. If you want, you can note down a short note, summarize. Let's move into the tute. What is given as an experiment? Okay, this is a simple practical. That's a nichrome wire. The nichrome wire of beaker containing coconut oil set up to circuit with a current regulator, ammeter, and it's connected to an ammeter. both ends of coil as shown in the figure. Okay. Okay, now what happened? Okay, now the current is flowing through this nichrome wire. Okay, if it is heated, this now it is a conductor. Nichrome wire is a conductor. It's a good conductor. When increase the temperature increase, when increase the temperature of this coconut oil, what happened? The ammeter value, the current flowing ability decreasing. What's the reason? With temperature, the resistance of the nichrome wire increasing. Okay, that's the observation of this simple practical. Okay, that's the factors effect of heating effect of the electric current. Okay, they are the main factors: current, resistance, and time. Current, resistance, and the time factors affected the heating effect. Okay, current changing, the current passing changing, and resistance changing, and time, that effect on the time. Okay, according to that, we have simple equation, the heating effect. H equal I squared RT. Okay, that's not a very important equation, but our syllabus, it has mentioned. Make a halana exam. H equal I squared RT. Remember, that is a heating effect. The amount of heat generate the unit joules. Okay, the unit joules. It's a heat, no? The heat equal I squared RT. Okay, that's not important. Come to next part. When a potential difference, that means voltage, right? Potential difference is applied to various electrical devices. If a current flow for period time, the energy generated by it. Okay, I will explain very simply this story. Okay, the heating effect completed. We have equation, the amount of heat generated on a circuit or conductor, H equal I squared RT. Okay, H squared, the heat amount equal I squared RT. In question discussions, you can understand. Hi, part. Okay, our next part, electric power. Electric power. What's the meaning of electric power? Electric power, P. What's the meaning of electric power? In power we discussed in work energy lesson, right? What's the meaning of power? The power means work doing rate, the amount of work doing in a unit type. Okay, the same thing. Remember the electric power, we have very simple equation. The power equal VI. මේටිකේ තියෙන equations ටිකක් විතරයි. හරිද? P equal VI. We have a very simple equation, P equal VI. What's the meaning of P? Electric power, not mechanical power. In work energy lesson, we discussed about mechanical power. This is electric power. Electric power equal VI. Voltage into current. Electric power equal voltage into power. Sorry, voltage into electric current. Voltage into electric current. Okay, now you already know we have simple theorem, Ohm's law equation, V equal IR. According to V equal IR, that's mean Ohm's law. We can modify this. That's the basic equation. Okay, that's the basic equation. The power equal VI. The power equal VI. Take your but phone charger. Can you find your phone charger? It's not clear. It's iPhone charger. Yeah, you can find input. Input කියලා එකක් තියෙනවද? Send me message. Can you find as input in the given description? Input. Okay, how about the input voltage in a charger? Input voltage. That can be changed. That's why I'm going to check. How about the input voltage? Input voltage 100 to 240. No, 100 to 240. 100 to 240. My one 200 to 240. 200 to 240 mean that's made for Sri Lankan condition. 100 to 240 mean any country that we can use. Product country will pull on. Input. Normally, how about voltage of in Sri Lankan home house? Voltage, it's 240. No, 240 to the 230 to 240. 230 to 240 voltage. That's the Sri Lankan range. But in different countries, it can be changed. Okay, how about input current? Input currents. Now, what is the value? 100 to 230. 100 to 230 voltage. How about input current? Input current. Input current. Input current. Input current. Input current 0.15 ampere. 0.15 ampere. Now you are plugged into 230 voltage. No, you are plugging your charger into 230 voltage, right? 230 voltage into the current 0.15 ampere. Now you can find your charger input power. How about the input power? Hari, 1 to 1 that can be changed. 230 into 0.15. In my one, 0.6. 0.6 ampere. Okay, what's the input power? Input power 23 into 6. 23 into 6. 138 watt. 138 watt. Okay, that's the input power. Input power. Okay, go to the output voltage. What is the output voltage? That's the input. Okay, go to output voltage. Out. Output voltage, it's 5 volt. In my charger, it's 5 volt and 3 amperes. No, 90 volt. 9 volt. 9 volt and 2.22 amperes. 2.22 amperes. Okay, then what is the output power? Output power equal power out. What's the value? It's 20 volt. Okay, normally when you buy a charger, they called 20 watt charger, 30 watt charger, 60 watt charger. That's output voltage into output current multiplication value. That's the power. Understood? That's why I want to explain. Understood? Okay, what's your charger output power? What's your charger output power? My one is 20 watt. Phone charger. This Samsung one, I have Samsung one. Its output power 15 watt. How about your one? You can calculate 30 watt. Okay. 5 watt. Are you sure, Kabi? What is this charger model? Samsung. 5 or 15. Then it will be very slow, no? 5. Okay, others? Rehlan, what's the output power of your charger? Tanya, did you check? Output 5 volt, 9 volt, and 12 volt. 3 in 1 adapter. Yeah, that depend on your phone. That depend on your phone and cable. Cable performance. The adapter is okay for all conditions. Yeah. Mainly charging speed is depend on your charging cable. What is the output current? Rehla? Output current? Dehini, did you check? $15 watt. Good. Okay, what's the meaning of this 15 watt, 20 watt, 30 watt, 50 watt? What's the meaning? Within 1 second, the adapter can provide output 15 joules. That's the meaning. 15 joules of electric current output. That's the meaning. Within 1 second, second 15 joules they can out. It can out. The adapter can out 15 joules. If you use now 15 joules mean it's a moderate and so normal average level. If you got more than 20 watt charger, that means within, if you got 30 watt within 1 second 30 joules output, then it's a fast charger. It's a fast charger. I got the point, Dihini? Okay, that's the meaning. That's all you want to understand. Okay, now how to calculate the electric power? Electric power equal current into voltage. Current into voltage. P equal VI. P equal VI. Okay. Now, okay. Okay, what I told, we have three equations for electric power now. We have three equations for electric power. P equal VI, P equal I squared R, P equal V squared over R. P equal V squared over R. Okay, that's a summary. Okay, now the work or energy. The energy transformation is a work. Okay, if you get the energy amount, how to calculate this energy? How to calculate the energy? Okay, remember energy equal the electric power multiplied by the time. Power multiplied by the time. Okay, you have very important two equations. P equal VI, that's the electric power equal current into voltage. The electric energy, it is equal to PT, power into time. Power into time. PT, power into time. Electric energy equal power into time. Okay, the power equal, we can modify this equation also. E equal P into T, then P, instead of P, I can use VIT. 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 Energy equal, electric energy equal VIT. VIT. Again, we can say electric energy equal I squared R. I squared R mean I squared R mean P into T. The equations. Okay. Same equation. Equations we have only two equations. E equal PT and P equal VI. Other all are modifications. Derived equations. Okay, final one. E equal V squared R T. V squared R over R T. Okay, they are the equations. W mean electric energy. E කියන්නත් පුළුවන්. EOW. EOW. EOW, both correct. EOW. E equal PT. E equal PT. Or W equal PT. That's the energy. Energy generated by any electric device. That's power multiplied by time. Power multiplied by time. Okay. Okay, that's a summary of electric power and electric energy. At the end of the lesson, I hope to I will explain the electricity bill calculation. For electricity bill calculation, you need those all relationships. Okay, therefore you can practice before we move into end of the lesson. End of the lesson part, after complete transformers, I hope to discuss about electricity bill, how your electricity bill in your home calculated, what's the meaning of electricity unit. Okay, for those all relationships you need this equations, and you have to remember it. Okay, let's start magnetism. Okay, that's actually today's lesson. That's a summary. Okay, ready for start the electricity and magnetism relationship. Okay. The relationship between electricity and electric energy and magnetic energy. Okay, that has a it's a close relationship. It has close relationship between this electric energy and magnetic energy. Okay, what's the relationship? Okay, if you got, I think you have done these practicals, this experiment, simple experiment in your grade 5 to 6 time. Okay, this is a normally we can use nail or iron rod for this experiment. Then you can make as a better to use copper coil, copper wire, copper coil, and make as a coil, make as a coil. Then you can switch into a battery, connect into a battery. When you switch on this circuit, what happened? Electric current flowing through this coil. Electric current flowing through this coil. Then what happened? Magnetic field is generated on this iron rod. Then if you use a small iron rod, what happens? It has attraction. Make an attraction. Then magnetic field. Then you can understand when current is flowing through a conductor, a magnetic field is generated, right? A magnetic field is generated. Okay, I will show you this experiment. It's a very simple experiment. When current is flowing through any circuit, magnetic field is generated.
I want to share my culture with new friends from around the world and feel.
Here we have an electrical wire with alligator clips, a battery, and a metal nail. How can we assemble these components to make an electromagnet that can attract some paper clips? Let's connect one end of the wire to the battery and wrap the wire around the nail. Now connect the other end of the wire to the other end of the battery. Cool, we've made an electromagnet. Test the electromagnet by moving it close to the paper clips. Nice, some of the paper clips are attracted to the nail. Disconnect the wire and the paper clips fall away. How can we increase the strength of the electromagnet so that it attracts more paper clips? Check the related videos to find out.
Okay, understood? Yes. Then what we can what we can get the conclusion. Okay, then you should have understand. You can understand when current is flowing through a circuit or any conductor, what happened? Magnetic field is generated. Magnetic field is generated. That's why we call this magnetic energy and electric energy has very close relationship. When current is flowing through any conductor, a magnetic field is generated. Magnetic field is generated. Okay, if you got magnet, it has two sides. It has two parts. The one side we called as North Pole and other one we called as South Pole. And N and S. Okay, think this is a magnet. This is a magnet. It has two sections. This is S and N. That we called as North Pole and that we called as South Pole. If you got the electric field, magnetic field, the magnetic field always generate. The magnetic field of any magnet, it always generates from North Pole to South Pole. Okay, that's the direction always. Please remember. Always the magnetic field is generates from north pole to south. That's very important. North to south always. North to south. Okay, that is the magnetic field direction always. The magnetic field always generate from north pole to south pole. See, north pole to south, north pole to south. Samely, north pole to south. The previous experiment also, the magnetic field is generate. The direction is north pole to south, not south to pole. South to north, north pole to south is the electric magnetic field generate, magnetic field direction. Magnetic field direction. Magnetic field direction. Okay. Now, if I place any conductor on a magnetic field, yes, if I placed any current flowing conductor on a magnetic field, what happened? Now understand. May I? Wait. If we supply current into a conductor, it generates magnetic field. Samely, now this experiment, now we have provide current and perpendicular to this current, this is a magnetic field. Okay, let's see this experiment. To understand this experiment, then I can explain easily. Okay, let's see this practical. Give me a second.
Two straight copper rods, which are connected by a piece of loose copper wire, complete a simple series circuit which will carry a large direct current. The loose wire is resting between the poles of the magnet. There's also an ammeter in the circuit. When the circuit is switched on, a very large current flows. Loose wire is then flicked out from between the magnets. Because the movement is sudden, it is sometimes called the catapult effect. If we take the magnets off and reverse them so that the magnetic field is reversed, and then rearrange everything else, then the wire is catapulted in the opposite direction. When the direction of the field is reversed, the direction of the movement is reversed. The diagram here shows a side view of the arrangement. Well,
Okay, could you understand? Okay, I will explain very simply. Okay, that's the story. If we supply electric current into any conductor, it generates electric field. Now that you already know. Now we are going to place electric conductor with electric flow, current flow, conductor with current flow, right? Conductor with current flow. Okay, this is a conductor. Now conductor, now the current is flowing through this conductor. Now this is a magnet. This is a U called as U magnet. Then think it is N and this is S. Always the electric field is, what is the direction? N to S, the north pole to south pole. Can you see some force is generated? Okay, when we place electric conductor perpendicular to magnetic field, we can observe, we have a result. One force is generated. Force is generated on the electric conductor, right? The force is generated on a conductor. But when we change the direction of the magnet, what happened? When we change the direction, mean electric field direction changing. This is a conductor. The electric field direction changing. Electric field direction changing. Now what happened? The force direction changing. Okay. Now we are going to investigate how this force is generated in a magnetic field. When current is flowing through conductor, how this force is generated, how to form this, and how the change of how to direction change, and how we can find this direction, and what are the usages of this force. Okay, they are the parts we are going to discuss now. Okay, now you can watch this video again and you can get full idea. Okay, this is a U magnet and this is a conductor. This is a conductor now. This is a conductor and there is a battery here in right side.
Complete a simple series circuit which will carry a large direct current. The loose wire is resting between the poles of the magnet.
Okay, this is a battery and it has connected to a ammeter.
When the circuit is switched on, a very large current flows.
No, it's a multimeter.
The loose wire is then flicked out from between the magnets.
The force is generated into right side direction, right? Force generated into right side direction. But
because movement is sudden, it is sometimes called
force generated into, see?
If we take the magnets off and reverse them so that the magnet
change the direction, change the magnet direction. Now what happened? Magnetic field direction changed. Now it is outside.
When the direction of the field is reversed, the direction of the movement is reversed. The diagram here shows a side view of the arrangement. Round circle represents the wire with the current coming towards us. The magnetic field around the wire carrying a current is clockwise looking in the direction of the current. Since it's going towards us, then it is anti-clockwise. Okay, this is the magnetic field direction always. This is the two magnets, they are the two magnets, and this is the magnetic field direction, N to S. The magnet runs from north to south. Fields between the two magnets interact. On the left, they both run in the same direction and reinforce one another. On the right, they run in opposite directions and tend to cancel out. The magnets are massive and are not free to move. The wire is light and gets flicked out of the magnetic field. The thrust takes it away from the strong field and towards the weak field as the system tries to reduce the concentration of magnetic flux on the left. Notice that the field, the flux, and the thrust of the wire out of the field are all at right angles.
This part that we can discuss. Okay, any doubt up to this level? Any doubt? Any doubt? Okay, let's read. If the above activity, the direction of the magnetic field and the direction of current flow in the conductor are arranged to be perpendicular to each other. Yes, current flow into perpendicular to the magnetic field. See, as experiment, this is a magnetic field. The magnetic field is always N to S, right? N to S. Okay, this is a magnetic field always. The magnetic field perpendicular to the current flowing direction. See, it's perpendicular. Vertical and horizontal. It's perpendicular to the current flowing direction. That's important. Can you then observe that the moment is perpendicular to the both direction of the magnetic field and the direction current flow. The magnitude of the force generated here depend on the following three factors. The magnitude of the current flowing of the conductor, that means the current magnitude. The current magnitude, we are discussing about this generate force. Okay, the magnitude of this generate force, the force, you know, now you should have idea when we place perpendicular magnet, when we place electric conductor perpendicular to the magnetic field, a current is generated, a force is generated. When we place, think is a magnet. When we place current flowing conductor perpendicular to this magnetic field, what happened? A force is generated. The magnitude of this force depend on following factors. Okay, the first one is the magnitude of the current. The second one, the length of the conductor. Placed in a magnetic field, and the strength of the magnetic field. That we called as magnetic flux value. Magnetic flux value. Okay. When these three factors increase, the resulting force exerted increasing. Yeah, all are directly proportional. That means what are the factors affect on this force? Okay, I will summarize. Okay, let's summarize this. This is a very simple part. When we place electric conductor perpendicular to any magnetic field, then force is generated on it. The magnitude of this force depend on three factors. What are the factors? The current value, current I, and the length L, and magnetic field. That means B, that we call as B. Magnetic field that we call as B. Okay, when these all factors increasing, what happened? All are directly proportional. May mono value not. What happened? The generated force is increasing. The force is increasing. Up to now, okay? Dehini, Tanya. Only 2 points I explained. When we place electric conductor perpendicular to magnetic field, the force is generated. The force magnitude depend on those three factors. All factors are directly proportional. Directly proportional can එකක් වැඩි වුණොත් force also increase. Okay, up to now, okay? Up to now, okay. Dihini? Fatima? Sarmia? Up to now, okay. Anything? Any doubt? See? In other form, when this any factor decreasing, the resulting exerted force decreasing. That's okay, and that's the directive proportion. That's mean the resulting force is proportional. That means not only proportional, directly proportional to about three factors. About three factors. Okay, now I want to calculate the magnitude of this force. Okay, therefore we can get equation, the magnitude of the generated force in a magnetic field, that is BIL, F equal BIL, F equal BIL, F equal BIL, F equal BIL, because all are directly proportional. That's why F equal BIL is a F equal BIL is a equation. F equal BIL is the equation. Okay, ET students, do you know what's the unit of B? That B mean magnetic flux density. I mean current. L length, no. Okay, do you know, ET student, do you know what's the unit of magnetic flux density? Magnetic flux density. That mean magnetic field magnitude. That's a measure of magnetic field magnitude. Okay, anyone? Do you know what's the unit of magnetic field, magnetic flux density B? Remember, it is T is the unit. The resulting force Newton. Okay, that don't need to consider. That's Newton. Newton is a unit. Magnetic flux density, it's T. Tesla. 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 Good. Tesla. I, current, ampere. L, meter. They are the units. They are the units. Meter, ampere, Tesla. Tesla mean capital T. Capital T. Tesla. Magnetic flux density, Tesla. Okay, now magnitude okay, right? Magnitude okay. If I place electric conductor with current flowing perpendicular to any magnetic field, a force is generated. Okay, that's the concept. This force magnitude we can calculate. There are three main factors affect on the magnitude: magnetic flux density, length of the conductor, and current magnitude. Okay, multiplication of those values, we can get the magnitude of the exerted force. That's F equal BIL is the equation. F equal BIL. Okay, magnitude okay. The force magnitude I got, but I want to get the direction as well. Okay, for direction we have to use Fleming's left hand law. Fleming's left hand law. Fleming left-hand rule. Fleming left-hand rule we can use to find the direction. Magnitude F equal BIL. Direction Fleming's left-hand law. Okay. Fleming's, what is the Fleming's left-hand law? What's the Fleming's left-hand law? If I place, okay, first read, when the thumb, index finger and middle finger in the left hand, Hadagan, you have to practice this. Your thumb finger, index finger and middle finger, you have to place in perpendicular. Hand are held perpendicular to each other. Please practice. You have to practice this. You have to make a perpendicular one on the middle finger perpendicular to, see, middle finger perpendicular to index finger perpendicular to thumb. That little bit difficult. Left side, left hand, not right. Left hand, only get these three fingers perpendicular to each other, like this. Okay, if we keep it perpendicular to each other and middle finger position to the direction of current. Yeah, middle finger always current flowing direction and the index finger position to the magnetic field direction. Okay, the direction which the thumb points is the direction is the force exerted. This is the force exerted direction. Okay, simply if you place the middle finger, thumb finger, index finger and middle finger perpendicular to each other, and if you place middle finger into current flowing direction and index finger into electric field direction, sorry, magnetic field direction, the thumb finger given the force exerted direction. Okay, this is a summary. This is a force, this is a magnetic field, and this is the electric current. Okay, you have to remember these fingers and name. What's the middle finger? What's the middle finger? Sandy? Middle finger? Tehlan? What's indicated by middle finger? Middle finger. Okay, middle finger. What? The electric? Yeah, the direction of current. Index finger? Yes, very good. Electric? Sorry, magnetic field direction. Thumb finger is, if you place these two fingers, middle finger and index finger into correct direction, the thumb finger given the correct force direction. Okay, let's practice. Let's practice. Okay. Now, how about the current direction of this one? How about current direction? This is the current direction. Current always pass into positive to negative direction. Okay, therefore this is the current direction. 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 N to S. N to S. This is a magnetic field direction. And current is flowing to this direction. Into this direction. And magnetic field, how about magnetic field direction? Into downward. Okay. Now you have to place your left hand, index finger into magnetic field, and this is the current direction, this direction. Now you can see this is the force exerted direction. Force exerted direction. Understood? Understood? Kabir? But the problem is, now if you got this Fleming's left hand law, this is the middle finger, index finger and thumb finger is the current direction, magnetic field direction, that's the force exerted direction. The problem, if you want to draw this structure, it is in 3D shape, no? This is may direction, it is into front direction, it is into upward direction. That is in now 3 factors, it is in 3D. Therefore, we can't draw these structures in 2D plane. I can't draw these structures in board because our board is 2D. Okay, therefore, I'm going to convert our circuits into 2D shapes. 2D shapes. Okay, this is a method. This is a method. Now, you have to think as a arrow. Arrow එකක් විදිහට හිතන්න ඕන. Okay, if you got arrow going away from you, arrow ඊතලයක් going away from you, then what you can see? You can see only this type mark, no? Arrow going away from you. Understood? මෙහෙමද පේන්නේ? Arrow going away from you. Okay, think arrow come towards you. Then what you can see? Rehlan. Arrow coming towards you. What you can see? මොකක් වගේද පේන්නේ? Towards you. මෙහෙම බැලුවොත් මොකක් වගේද කබීර්? What's the shape? Now arrow coming towards you. Yeah, it's a point. Point එකක් වගේනේ පේන්නේ. Okay. Okay, now in 3D forms, in circuits, no problem. But in our drawings, we can't do this application in our board. That's why I am going to use this method in exam also given in this form because exam paper also 2D. Okay, now this is a magnetic field. This is a magnetic field. Magnetic field going towards to going into the plane, into the plane. Into the plane mean inside to the plane. Magnetic field inside to the plane. Then Fleming's left law, Fleming's left hand law, you have to use as this. Fleming's left hand law. Magnetic field inside to the board, inside to the board, inside to the board. Okay, what is the meaning? The magnetic field coming outside to the surface of plane. Understood? This is outside, come towards us. Clear? 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 Then that's a method you can use Fleming's left law, left hand law. Outside. It is inside. It's away from us. The arrow away from us, arrow towards to us. Understood? Dini? Fatima? Samya? Hudanna? Tanya? The arrow away from us, the arrow towards to us. Now, this is the conductor. The current is flowing into this direction. Current is flowing to this direction. Can you find the direction of force? Hurry. First, you can draw this. You can draw. Please draw this both magnetic fields and write down magnetic field going into the plane and magnetic field coming outside to the plane. Okay. Can you find what is the direction of this conductor? AB conductor. What's the direction? Okay, I will help you for first one. Okay, now what is the magnetic field direction? This is a magnetic field direction inside to our board. In your case, inside to your book. Okay, inside to your book. You have to practice. You have to practice this. You have to practice. Okay, now this is the magnetic field direction. Magnetic field direction. Now, how about current direction? Current direction left to A to B. A to B. Okay, now how about the direction of the force into upward direction? This is a force direction. F. Understood? Simple. Simple. Sarmya? Understood? Joel? Termal? Okay, may to manage your fingers. I know you can't, still you can't, but you can practice this. මෙහෙම බෑ ඔයාලට මම දන්නවා තාම. But you can practice. Keeping all three finger perpendicular, you can practice this. Now rotate කරා නම් පුළුවන් නම් okay. Okay, AB. This is the current direction. Okay, what is the force direction? Quickly send me. Upward or downward? Rehlan? Now arrow come to your side, towards to you. Dihini, what is the direction? Tanya, Samya, Udanya. No, Sarmya. Try again. Magnetic field into your direction, Sarmya. That means outside to the book. Outside from the book into your side. Then, okay, simple. Now this is the magnetic field. It's come to your direction. Now this is a magnetic field, and this is the magnetic field. So the magnetic field into your direction. Make a perpendicular තියාගන්න ඕනේ. Magnetic field into your direction, and this is a current direction. Then how about the force direction? Downward. Downward. This is a force. Sarmya, you have to practice. Okay. PQ. The current flow into downward direction. right or left? What is the force exerting direction? What's the force exerted direction? The magnetic field inside to the board or inside to your book. Very good, Rehan. This is a magnetic field direction inside to board. This is a force direction, sorry, current direction. Then right side. Good. Right side. This is a force. Okay, this is another conductor. PQ. PQ. This is the current direction. Okay. Second one. What is the direction? Salmia? Good, Rehan. Okay. What's the field direction into your side? Current into downward. Current into downward. Then how about the direction? How about direction? Into this direction, left side. F. Okay, go to a tutorial pack. In tute pack, I added few questions. I can't remember what's the tutorial. First one, tutorial number 1, final page. Is the tutorial number 1, final page. Tutorial number 1, final page. This sum. Okay, first one, calculate the direction. Sorry, no, find the correct direction of force exerted. First start, quickly send. Left or right or down or up or down. Okay, the field into your side. The current flow into right side. Then force downward direction force. Okay, second one. Current, sorry, magnetic field into your side. The current into left side direction, then it's upward. F. Okay. Question number 3. The magnetic field into both direction away from us. The current direction into upward. It is left side. Okay, current magnetic field direction same. Current direction into left to right. Then it is upward direction. Okay, this finger behaviors you have to practice. To keep perpendicular you have to practice. මේම කරන්න බැරි කවුරු හරි ඉන්නවනම් please send me message. If you can't keep these fingers perpendicular to each other. මේම කරන්න. That's direct one, upward, and keep perpendicular 90 degree. Understood? Any doubt? Udanya? Clear? Third one. The magnetic field into away from us, that means inside the board. The current flow into upward direction. This is a force. Okay. Any doubt up to now? Okay. Okay, do you know what are the applications of this force exerted when we place current flowing conductor perpendicular to the magnetic field? A force is generated. Okay, what are the applications? Do you know how to motors working? How to fan and motors working? That's due to this. Okay, that's a simple motor or fan. I will explain how to work this fan or motor. Okay, now if you observe the inside of the motor, parts by part, if you removed and if you observed, you can see it has two magnets. It has two magnets and it has a copper coil. It has copper coil in this shape. Okay, this is the shape of this copper coil. This is the shape of this copper coil. This is the shape. Okay, this is the shape of this copper coil. Okay, Now tell me, this is the inside of the magnet, this is the south pole. Okay, how about the magnetic field direction? How about the magnetic field direction? How about magnetic field direction? N to S. This is the magnetic field direction. This is a magnetic field direction, right? This is a magnetic field direction. This is a magnetic field direction. Okay, now if I connect this, now I am going to plug this fan into battery or normal voltage. I'm going to supply voltage. Okay, now what happened? The current is flowing this direction. The current start flowing from this direction. Mehin current එක flow වෙනවා. Current flowing I. Current flowing positive to negative, right? Positive to negative current flowing. Okay, if you got, now think about this part. Now only think about this part, this section. This section when make විතරක් හිතන්න. Now what happened? According to Fleming's left hand law, this is a magnetic field direction. How about the current direction? Current direction into upward. Current direction into upward. Now what happened? Force, a force exerted inside to the, inside mean into front direction, right? Into front direction. මෙහෙට force එකක් එනවා. Understood? This is F. Understood? Tehlan, clear? The force on this side, a force is exerted into inside direction. Tehlan, clear? Samya? Okay, now බලන්න. Now the same current flowing through this path as well. Now what happened? This is the magnetic field direction same, but current direction changed downward direction. Now what happened? Force exerted to this direction. It is exerted to this direction. මෙහෙට. Not downward. Downward නෙමෙයි ඒක මේ. මෙන්න මේ පැත්ත. Perpendicular to surface. I can't draw this. Okay, I will draw in this way. F. Okay, now that we call same force, same magnitude, two forces exerted into opposite direction in two lines. What is this? That's a couple of force. Couple of force. Then what happened? It's rotating. That's the reason. It's not a rocket science. Very simple science. Any doubt? Okay, that's. Do you know how to use this copper coil with many number of turns? Make a local coil එකක් තියෙන්නේ. ලොකු පොටවල් ගානක් තියෙනවා. What is the reason? To increase the magnitude of the force. You know, the F magnitude equal to BIL, no? BIL. Length increasing, what happened? Force increasing. Current increasing. If we going to use, if you're going to increase the current, it use more current energy. That's not a good thing. That's why we can increase the length of the copper wire. ඒකෙනුත් අපිට වැඩි කරගන්න පුළුවන්. Then we can give normal current and powerful magnets. Two powerful magnets. Then we can get super force. Any doubt you can ask? Okay, if you have any doubt, you can send me. I will give you 30 seconds.
Introducing Rebello Valentine's limited edition with butterscotch.
Working principle of DC motor. Working principle of DC motor is very simple. We can see that when the current conductor is placed in a magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet, an elementary model. One single turn of conductor.
Okay, this is a structure. They are the north pole and south pole. Then always magnetic field north to south, and this is a battery, and current flow into positive to negative.
Is placed between two opposite poles. If we start to supply DC by commutator system, current will start to flow. As we see, positive terminal of the battery is connected to the left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they place in magnetic field. Both of them experience mechanical force acted on them. Current in the right side flows outward. As we see,
Okay, this is a magnetic field.
Current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, if the forefinger is aligned along direction of magnetic field from north pole to the south pole, and second finger is aligned along direction of the current and left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field from north pole to the south pole, and second finger is aligned along direction current and right side conductor, then thumb indicates direction of the mechanical force. Due to this upward and downward force is on the turn.
Okay, that's how it's rotate. That we call as couple of force. Same magnitude, two forces act in opposite directions. Any question? Give me a second, Elan. Two same magnitude, two forces act in opposite direction in two lines. That's couple of force. That's how it's rotate.
I'm torquing.
Wait. Okay, I'll explain after that.
To produce when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position, there is no current in conductor because conductor, and brushes rest between two commutators. Hence, there is no force acting on conductor due to moment of inertia. Turn continues to rotate and comes horizontal again. Position of conductor has been changed here. That means conductor, which was previously in left position, comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one to another. So if forefinger is aligned in direction of magnetic field, that is, North Pole to South Pole, and second finger is aligned in direction of current in the left side conductor, then thumb indicates direction of mechanical force.
Same thing, no?
This is clearly upward here. So if forefinger is aligned in direction of magnetic field, that is, North Pole to South Pole, and second finger is aligned in direction of the current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. To do this upward, and downward forces tend to rotate in clockwise direction. From that explanation, we can come to conclusion that here in this model, we can see that whichever conductor comes near South Pole experience upward mechanical force, and near North Pole, downward mechanical
Okay,
force.
that's how a
And
simple motor is working. Okay, that's okay, let's try to discuss Fleming's right-hand laws. And then we have only transformers now. Okay, let's try to quickly complete. Okay. That's the Fleming's left-hand law, or Fleming's the force exerted experiments and applications. Okay, final one, electromotive induction. Electromotive induction means yes, electromotive induction means now opposite side. It is a magnetic, not magnetic. It is a, yeah, this is a magnetic. This is a magnetic. This is a magnetic. Now that's another experiment. If we move this magnet close to this conductor coil, make up move karot, we can see any very small changes in ammeter. We can see small changes in ammeter, that very small rotation. That means when we move, or when we change the position of any magnet close to electric conductor, a current is indicating. That's the meaning of electromagnetic induction. A current is the current is forming, generate when magnet moving close to electric field. Okay. Okay, observe the rotation of the galvanometer in each of the following cases. Bring the north pole of the magnet close to the coil, keeping the magnet stationary near the coil. If it is stationary, no any result. Moving the magnet away from the coil. change in the speed at which the magnet is moved, increase in the number of turns in the coil, and bring in the magnet closer. Okay, there are different tests, different experiments. Okay. Different experiment. Okay, this is the result. When there is no relative motion between the magnet and coil, no current is flow, no current is forming through the coil. Okay, that's the result. But when it is moving, relative motion එකක් තියෙද්දි a current is flowing. A current is flowing. We can observe in this experiment. Okay, that's the final result. When there is relative motion between magnet and coil, a current flow through the coil. Yeah, that's the final conclusion or result. The direction of the current change depend on the direction of the motion of the magnet. When change the magnet motion direction, the current flowing direction also changing. Then it has a considerable point, right? The current increase in the moving speed increasing. When increase motion speed, the magnitude of the current increasing. Then we have evidence when change the position of any magnet in a magnetic electric field, a current is forming. Okay, Fleming's right hand law is very important. Find the direction of electric current induced in this way. Okay, the Fleming's right hand law we can use to find this current direction induced by in a magnetic field. The current, why we use Fleming's left hand law? Left hand law used to find the force direction in a magnetic field. The Fleming's right hand rule where we used to find the current direction. Okay, let's see what is the Fleming's right hand rule. When the index finger, thumb finger, and the middle finger arrange in perpendicular way on right hand, the index finger position to the direction of the magnetic field, same. The index finger magnetic field, same as left hand law. Index finger into magnetic field, and thumb finger position to the direction of motion. Thumb finger now not force, it's motion direction of the magnet. The direction of middle finger indicate the current direction, same as previous left hand law. The middle finger is the current direction. Okay, this is a summary. This is a motion direction, thumb finger, the magnetic flux direction, and electromotive force mean the current direction. The current forming direction is the middle finger. Middle finger is the current direction indicate. Okay, the applications. Okay, let's practice Kirchhoff. Let's practice Fleming's right hand law. Fleming's right hand law. That's very simple. The opposite. Okay. Okay, magnetic field similar. The cross marks mean the magnetic field toward to the surface. Dot marks mean magnetic field toward to us, outside from the surface. Okay, this is the wait. Have dot. Okay, this is a magnet. This is a moving direction. Can you find the current? Now I'm going to think it is AB conductor. AB conductor, the conductor is moving in a magnetic field. Conductor is moving in a magnetic field. That one also same. The current is flowing in the conductor. Okay, what do you think? What is the current direction? Now Fleming's right, current direction by right side, right hand. Okay, what is the current direction? Inside to the surface, inside. What is the force? This is a force direction. What's the force? Then it is, this is the current direction. Understood? Rehlan, Dihini? Same thing we doing by right hand. That's only difference. Tanya? Salmia? Okay, please find the this is a PQ conductor. This is F or motion direction. Okay. Can you calculate the electromotive direction, not electromotive or current direction? Quickly. Downward or upward? Sarnia? Okay, right. Use right hand. The magnetic field inside to the board and the yeah, the force into right side, it's upward direction. Good, Sarmi. Upward direction. This is a current. Okay, this one. AB. Please find the current direction. A to B or B to A. A to B or B to A. Okay, now use right hand. Right hand. The magnetic field into your side and force into downward. Force into downward. Then what is the direction? Into B to A, no? B to A. I think now it's easy. Okay, let's go to tutorial questions. Okay, first one, question number 5. Question number 5. It's given. Answers given. Sorry, it's answers given. Current direction එක දීලා නේද? Okay, let's check they are correct. හරි අපි හරිද කියලා බලමු. Okay, the right hand, I'm going to calculate the current into this direction and force into upward direction. Then this is a current direction. It's correct. Correct. Okay, this is the force direction. Sorry, magnetic field into outside. Outside, this is a current direction. Sorry, this is a force direction. Yeah, this is a current direction. Correct. Right side. Ek dila තියෙනවා. 7. 7. Use right hand now into our direction. Force into downward. Then force into downward, right? Then this is a direction. Yes. Force into your direction, force into downward. Yeah, like this. Force into downward. Correct, right? Yeah, actually, right side is it will be difficult to me, but you can practice. Okay, towards the surface, force into downward. Yes, this is the current direction. Yeah, 6th one or 7th one? Yeah, please check this one, make correct. Make mata huru nae mehema. Downward. No, it is into opposite direction, right? Yes, it's wrong. This is a correct direction. Please check in your one. Okay, but Joel, question number 6. Question number 6 into opposite outside direction. Question number 6 into outside direction. Outside direction. The force into that one also wrong, right? Check. No, in book it is easy. මෙහෙම තියලා බලන්න පුළුවන් උඩට. But in board it little bit difficult. Yeah. Into a okay. The force into yes, opposite direction current. I. Okay, what are the applications of that? What are the applications of this? Do you know? The motion of magnet and produce electricity. Yes, turbines and dynamos, alternatives, all are use this method. Okay, this is a turbine. Okay, this is the homework today. This is a homework today. How to produce electricity. I already explained about motors and Newton's, Fleming's left hand law, everything, applications. Okay, you have to find this. This is a homework. This is a homework. You can find internet, YouTube, any tutorial. You have to find out. I have given some diagrams. Next week I'll explain. You have to find out what is the working mechanism of turbines and dynamos. Same thing, dynamos. By rotating a magnetic field, it produces electricity. They are the application. Okay, now you already know the concept. I want how to actually use that. Understood the homework? ඇත්තට මේක කොහොමද කරන්නේ? In practically, in physically, how to do this? Okay, you have lot of tutorials and lot of internet photos you can find out. Understood homework? Okay, that's like assignment. Okay. Okay, මේ වගේ simple explanation also given in YouTube. You can search about tutorial. Okay, I will ask in next day, next Sunday. You have ready for finalize the complete the electricity lesson next Sunday. Next Sunday 2 p.m. I am going to start electricity final part, transformers, to complete the lesson. After that, next Wednesday, I'll go to, I hope to get into question discussions of electricity lesson. Then that's the end of 18th of Wednesday, we can get for question discussions. Okay, that's the end of the next Wednesday is the end of the final day of electricity lesson. Okay, do you have any doubt up to now? You can ask now. If you have any doubt. Any doubt? No? Okay. Up upcoming month. So I will not be able to attend the night classes. Afternoon. Entire month, Rehlan? Is it entire month? Oh. Then, okay, don't miss any classes now. You have very limited time. Okay, then you have to watch recordings only for 4 weeks. Okay, let's see. Next month, no? March, right? Okay, let's see. 18th. Upcoming month or next week? 18th mean next week? This month. Okay. Okay, let's see. Okay, send me message. I will give you a solution. Okay, let's meet Sunday 2 p.m. Goodbye. Good night.